Okay, then welcome everyone to the weekly colloquium of the Physics Institute of the UNAM in Cuernavaca, Mexico. Our guest today is Professor Tillmann Kubis from the Purdue University in the United States. And let me say some few words on his vita. So Tillmann is currently the Silvaco Research Assistant Professor in the Elmore Family School of Electrical and Computer Engineering of Purdue University. He received his PhD from the Technical University in Munich in Germany in theoretical semiconductor physics in 2009. His early quantum transport software powers the quantum cascade laser, resonant tunneling diodes, and quantum well functionality of the commercial software Next Nano. Since 2011, he has been working on developing quantum transport methods and their numerical efficient implementation in highly scalable, industrially relevant simulation tools, collaborating with many semiconductor companies like Intel, Samsung, TSMC, Lumileds, IBM, Global Foundries, Hamamatsu Optics, and Silvaco. These tools allow to predict charge, heat, and spin transport in semiconductor, nanodevices, optoelectronics, 2D materials, and topological insulators. Tillmann Kubis is co-developer of Purdue's quantum code library and since 2018 has been leading the NEMO 5 development and its commercialization through Silvaco. And Tillmann Kubis is co-developer of the Ideas to Invention classes of the master's program in the Elmore Family School of Electrical and Computer Engineering. So Tillmann, thank you very much for joining us today, at least virtually, and we are looking forward to your talk.
Well, thanks a lot for the kind introduction and for the invitation to talk. So hello, everyone. And I'm happy to talk about the work of my team. It's all centered around quantum transport simulations, in particular for 21st century electronics, but also many other applications, as you will see in the talk. I'm really excited about quantum mechanics and quite happy to see how quickly it is evolving, particularly when you go back in history. Less than 100 years ago, the term quantum mechanics was introduced. And even just 50 years ago, it was a theory still used only by a small group of specialists. You can see that when you look at the number of publications on the topic of quantum mechanics. So 50 years ago, that was really marginal. And now, of course, it's increasing rapidly. And well, I hope it's obvious, quantum mechanics indirectly, at very least, is an essential part of our daily life. So those devices or gadgets that you see there in the background here, they are areas that my team has contributed to or is helping to develop. Just a few words about myself and the support of what we got. I'm research faculty since quite a long time, and that work automatically entails intense collaboration with industry. So here are some logos of companies that supported this work. In particular, I acknowledge, of course, the Silvaco company for the recent endowment of this work. So we, of course, work with them also quite a lot. But you will see that later in the slides. Working with industry, just to briefly show you what that means, and I maybe would like to also advertise this modus of operandi for everyone. We usually would start with customer interviews. So whoever you think your research idea would be relevant to, I would really suggest to talk with these people early on, write or propose to them what a product or a model, a simulation method or a research, whatever research approach should look like. You might want to de-risk that prior to the big proposal, and then hopefully you can apply for funded development work. So this is here a commercial version of that process, but I'm sure either intuitively or very explicitly you follow that already if you're faculty or a postdoc, and I think that's just the same approach in industry. Now with this research faculty position, I kind of do that on both sides, both industry and academia. All the work that you will see has followed this approach. So we had really hundreds and hundreds of meetings with industrial representatives and discussed with them a lot. And we still follow that approach by today. So about this presentation, the core physics method behind quantum transport is actually many particle physics. So I'd like to motivate why we would need many particle physics method. I'd like to showcase that these methods give really trustworthy results. They are transferable to many research applications, well beyond those specific ones you will see. So I give you some examples of transferability. I think they are a core reason why we have quite a lot of users already, why we can expand to material science. I will also showcase you how we expand to truly irregular systems, such as even liquids, and give a few comments what we are currently working on, like what will come in the future, is it the nearby future. Now, in all of those questions, I'm not going to do that only in an abstract way, but I would like to highlight all of those and answer those questions with a long list of different devices and device applications and materials. And whenever you see a box here with red circumference, then this is a publication that came out of my team, of course, for those specific applications. Okay, so let's get started. Do we need complicated many-particle physics for 21st century electronics? Well, modern devices such as nanotransistors and sensors and many others, they very often are very small. They have a very significant interface to volume ratio. That also has to do with increasing their susceptibility for any kind of external effect, like switching them or having sensor features as an interest. They come with a lot of quantum effects, and when you have interfaces, in particular between different solids, then you usually have a significant lattice mismatch. So there's irregularity in there, even if the phase of the material you're working with is actually solid. Now, nanodevices such as transistors, they run at fairly high power densities. So, energy and momentum transfer effects between different particle types, like maybe electrons, photons, whatever, they are very important. And in that sense, if you want to model those or, predict the performance of those devices, or maybe if you want to even improve the design, you have to cover all of those effects. And well, what we do in my team, we focus a lot, not exclusively, but a lot on the non-equilibrium Green's functions method. Why do we do this? Well, it's our understanding that the non-equilibrium Green's function method, by the way, that's typically abbreviated with NEGF. It's an excellent method to cover quantum effects such as tunneling, confinement, interference in real-world conditions. So that's, I think, an important point to stress. If you care about impact of finite temperatures, so statistics, varying device qualities, external effects and energy transfer and so forth, then NEGF is really one of the most powerful methods for that. That is so because it provides a consistent description of coherent and incoherent effects. And I think a key feature for that, in particular also for its numerical efficiency, is that it allows to separate an active device from reservoirs. Now, in a standard textbook example, you would learn about that by having the reservoirs as kind of geometrical reservoirs, like source or drain reservoirs that provide particles, or maybe at least some sort of propagation entities like quasi-particles. And obviously then the interaction of those reservoirs is described as self-energies. However, those self-energies, they can also cover the interaction with more, let's say, abstract reservoirs, and not necessarily just source and drain leads, but they can also describe the interaction with other particle types that would probably act as a heat sink or as a source of energy. So scattering of electrons with phonons or with photons, or even other electrons can be as well described as self-energies. And of course, also when you have uncertainties in your device structure, like scattering on impurities or roughness or any kind of disorder, then self-energies can handle that. So it's a very consistent way to incorporate geometrical aspects as well as energy and momentum transfer aspects. Now, to understand, at least on a high level, what the impact of self-energies is and how that makes NEGF differ from, let's say, the Schrödinger equation. So I try to explain it here in a simple high-level overview. When you solve the Schrödinger equation, you have a Hermitian eigenvalue problem at hand. So you would have a Hamiltonian with maybe some electrostatic potentials. Obviously, you have eigenfunctions and their eigenenergies. And whenever you have an eigenenergy here, just depicted here on the energy and the real energy axis, then at the same energy you would have a Dirac delta function in the density of states. So an infinitely thin and infinitely high peak. And of course, otherwise you would just have no density of states. So it's a very discrete result. Now, when you have self energies, usually you would solve the Kelvin and Dyson equation. So here is the Dyson equation given. That's in that sense similar to the Schrödinger equation, that you have here your free particle Hamiltonian, you have here this electrostatic potential. Now, instead of eigenenergies, you would have energy parameter that you are sampling yourself. So this is a free parameter in that sense. And well, you have to invert that matrix. So if you for the moment ignore the sigma r term, whenever your energy equals the former eigenenergy of your Schrödinger equation, you would get a pole, right? You would have a non-invertible matrix. Now, that doesn't fundamentally change when you have the sigma r, which is a retarded self-energy, but it shifts the energy at which you would have this singularity. So since these self-energies have an imaginary as well as a real part, they are shifting those resonances, those poles, into the complex energy plane. Now, well, of course, that depends again on the details of the physics of these self-energies. But in general, depending on the imaginary and the real part of the self-energies, those Dirac delta functions in the density of states, they also get shifted. So by two different energies due to the real part of the sigma r self-energy, and they get also broadened and get more shallow depending on how far in the complex plane or how far away from the real energy axis the new resonances are, the new poles are. So it's an important takeaway here that an EGF always gives you a spectrum, a continuous spectrum in the density of states. It never gives you just discrete numbers. Also important to mention, in particular, if you work on Cauchy equations, so maybe if you work a lot with DFT simulations, you might find that state broadening is an act of post-processing your data. This is not the case here. So these self-energies have to be consistently solved with the Green's functions. So there's no arbitrariness in that sense. You can't just say, I want to broaden that a little further. I mean, you can do that, of course. You can just assume specific self-energies, but as such, that's not necessary. The theory allows for a very consistent description between density of states and the broadening itself. Also there, it's important to mention the Cramer's chroniculations. So the imaginary and the real part of the self-energies, they are intimately coupled via the causality principle. So resonance shifts and resonance broadening, they are both coming out consistently of the simulations. Well, a complicated theory, or fairly complicated, is it worth it, right? Does it give trustworthy results? Is always an important question. Well, the first time I had to encounter that is long ago doing my PhD work. At that time, we were simulating transport of electrons through quantum cascade lasers. So not getting too deep into the shape of those lasers, but they are a sequence of hundreds of quantum wells and quantum barriers. So you have a lot of confinement effects, but you also have a lot of incoherent scattering in them. So it's really the playground, or one of the, I think, favorite playgrounds for something like an EGF. This was done in collaboration at that time with the TU Vienna. So they had provided us experimental data for a sequence of terahertz quantum cascade lasers. So you see here the current density is a function of applied voltage. The solid, I mean, these dots here, they are experimental data for those lasers. The solid lines were our calculations. And well, please trust me, at that time, we did not explicitly fit any parameter to the experiments. All the parameters we had to use came directly from literature. So, it was a very, it was actually very surprising how well this all worked out of the box. By the way, the difference here for higher voltages at that time, well, this comes because at that point, the terahertz lasers start to emit light. So we have the nonlinear optical regime, and that gives you a very intense electron-photon interaction. And that, long ago at that time, we did not include this interaction in the transport simulations. One important aspect to get this nice agreement with experiment, at least in my opinion, is to carefully validate your implementation of scattering self-energies. So here's just some examples for electron scattering on polar optical phonons. So here's the case here of bulk gallium arsenide. So out of that imaginary of the retarded self-energy, one can deduce scattering rates. And the benefit or the nice part about scattering rates, in particular in bulk semiconductors, is that you have textbooks with Fermi's golden rule results of those scattering rates. Obviously, we should be able to reproduce them with Green's functions, and yeah, one can faithfully do that. Here, by the way, you see two types of scattering. So here would be for low energies of electrons, the absorption of polar optical phonons. Then, of course, once you have enough energy, you can start emitting them. Deviations at higher energies, they always come usually at least at multiples of the phonon energy. So those are basically phonon echoes. And for instance, Fermi's golden rule is a linear response theory. These are, when you take textbook formulas, they won't cover those phonon echoes. So we've done throughout our development of code and formulas, we've done extensive validation on that regard. We've done it also, of course, for other geometries like ultra-thin bodies. By purpose here, I show you a spiky result of this NEGF scattering rate versus Fermi's golden rule. The fact here is, or that the reason for this spiky result is simply the Green's function method is typically considering scattering in position space, whereas Fermi's golden rule would always assume plane waves, basically, or some sort of wave, momentum space. So in order to compare them, one has to Fourier transform the NEGF results into momentum space. And of course, that is a matter of resolution. So those spiky results, they are a typical pattern you would get if you don't have a really high resolution, like very expensive, like numerically fairly expensive resolution to correctly transform the results. So it's just as a warning, if you want to do this validation work yourself, the validation itself can be even more expensive than the simulations you might want to do later on. Scattering rates are quite important for the work of my team and for those 21st century electronics. So state lifetimes, optical line width, tunneling probabilities, resistance, all of that crucially depend on an accurate scattering rate. Here's just some example for nanowires. So it's still the same scattering rate. In the case of nanowires, we don't have to Fourier transform, so we have a much easier way to compare the scattering rates. So you see here much smoother lines. Since this is maybe also here worth to mention, since we define self-energies in position space, when we have many band models, so we see here the when with many bands, of course, you get also several different valleys. So scattering between valleys in Fermi's golden rule would be considered inter-valley scattering. It's a different formula than intra-valley scattering. So that requires you as a physicist to understand at which energies, which of the mechanisms kick in. However, in NEGF, once you describe everything in position space, inter and intra-valley scattering are included automatically. So this agreement here did not have any tuning or physical insight on the side of the NEGF method. Obviously, it's quite a critical question once inter-valley scattering kicks in, because that will determine your valley saturation, the on current of many transistors. There's also another point I will mention also later again. If you look into NEGF literature, unfortunately, it is fairly common to ignore non-local scattering effects on the self-energies simply because they are numerically expensive. So word of caution, you should not do this kind of approximation when you have Coulombic or Coulomb-forced scattering mechanisms included. So like the polar scattering of electrons on polar optical phonons is very, very non-local in nature. And again, only because of that, we have this very nice agreement between the methods. Now, I've talked here a lot about validating the imaginary part of the self-energies. The real part has another important aspect. So to showcase that, you see here the density of states, again, as a function of energy in numbers here of optical phonon energies for the case of bulk gallium arsenide. So when you do a ballistic calculation without any scattering, you would have at some point The band edge is given here in the dashed line, and the 0 point is just chosen to agree with this. Now, if you just include scattering without a real part, you will see a band tail to form. Here there are also some phonon echoes visible, for the multiples of optical phonons, optical phonon energies. But yeah, the real part of the self-energy gives you, in addition to the tail, a significant shift of the band edge towards, in this case, your lower energy. So that effectively gives you a band gap narrowing. Obviously, that is a critical point for any kind of band-to-band tunneling devices, like tunneling field effect transistors, or if you care about optical transition energies. Also here, I have to say, unfortunately, the real part of self-energies is far too often ignored, most often because of numerical constraints. But you lose the information of bandgap narrowing for sure. Bandgap narrowing has another nice point because you can measure that in experiments. So here you see bandgap narrowing as a function of doping concentration for a baryc gallium arsenide when it's n-doped here at room temperature. The black results were our simulations. The different colors you see here, the dots, were taken from different experiments. Also here we had not to fit any kind of parameter. So this agreement literally came out of the box. We were also able to reproduce the characteristic doping dependence of the bandgap narrowing. Oh, and by the way, I would like to stress also the way we had implemented, details of course given here in this paper, the way we had implemented scattering on charged impurities is elastic. Still elastic scattering can give you, or can support band tail formation, which as such one would say is an inelastic process, as soon as there's enough inelastic scattering present. So it's an indirect, or it's an interference effect that gives this significant band gap narrowing. Yeah, I've mentioned the band tail. So the slope of the band tail is actually Urbach energy or Urbach parameter. So I just wanted to say this again, a parameter one can measure in various experiments. So just to confirm again, we get nice agreement with experiments here for the various cases without any kind of fitting. So as long as we have parameters that are validated already in literature, like band structure parameters, for instance, or dielectric constants, then yeah, we get this quite nice agreement. So this band tail parameter is critical again for any kind of tunneling through barriers, determining state line width or broadening resonance conditions. For engineers, it's important, for transistors in particular, it's important for how quickly a transistor switches, what the leakage current is, and how large the off current is. And please kindly refer to this paper if you, of course, care for more on the formula sides. And of course, there you find also data for many other materials. And also here again, right, non-local scattering is quite critical if you want to get this agreement. So just here is a quick example taken from this paper. So I don't want to shock you with the complicated formulas, but I'd like to at least explain why self-energy formulas can be comparably involved. So you see here the scattering self-energy for electron scattering on polar optical phonons in ultra-thin bodies. So those position coordinates, they are two-dimensional. We have one periodic direction, so you have a momentum parameter, and then of course energy. So the formulas are fairly involved. This function I here, basically a kind of scattering kernel. It even has here a modified Bessel function of first order. So this comes about when you care for numerically efficient implementations. So that would then require you to solve as many of the scattering integrals analytically as just possible. In quotes, the lazier you are on the analytical side, the more computational burden you put on the CPUs. So since we developed this here for industry, we really had to make sure that those simulations can run on an everyday basis, and then automatically have complicated integrals to solve analytically. Okay, well, great. It works for some bulk and maybe ultra-thin body semiconductor systems, so it's transferable to new research. Yeah, that gets me back to an experience I gained as a PhD student in Munich, and I've seen it also in many conferences with colleagues when I spoke with their, with them about their quantum transport implementations. Unfortunately, in the first moment, when you look at those equations, you might think they are fairly easy to implement. So at least it happened to me as a PhD student. But then when I had to apply them on different systems, like, I started with the quantum cascade laser work, then I went to spin transport, and then also atomistic tight binding. I ended up implementing 3 different versions of the Green's function method. Whenever you do that, you have again the problem of validating all the implementation and of course performance improving that. So when I came here to Purdue, I was fortunate enough to be allowed to introduce a new paradigm to avoid this re-implementation work. So we call it the propagation concept. The idea was we wanted to have an EGF implementation that is as general as just possible. So it should work for any kind of known and future device topologies, 4D maybe with a time domain or whatever. Then it should work for any kind of known and unknown particle types. It should not work for any kind of material, for any kind of representation of those particles, again, known or unknown, and for any kind of approximation. So the idea was, let's implement something that is as system agnostic as just possible, so that we don't run into this situation ever again. And well, it sounds ambitious, but there is a way. We found a way for doing that. So in order to explain that, I try to show you here a typical, well, let's say task list of objects you would have to produce in an NEGF simulation, maybe when you do some scattering and you do stationary transport. So you would have to solve the Dyson equation and the Kelvin equation. You would have to get a Hamiltonian with certain parameters. You would have to get contact self-energies and scattering self-energies. And of course, some of those are depending on other objects, and some of the equations you have to solve iteratively, like here the Kelvin equation, the lesser Green's function is depending on the self-energy, and that self-energy itself is again depending on the lesser and even also the retarded Green's function. But as such, you see here there's a lot of, there's a couple of boxes, so these are tasks, and there is some interdependencies. So in order to make the system agnostic, what we did is we translated these tasks into individual modules and made sure each module is system agnostic. We defined, proper input and output API for each of the modules, and well, with all these dependency errors, of course, the program flow might be quite difficult to set up. So we established a system of data on demand that would determine the program flow by itself, like automatically. And now having that modularized version of NEGF, of course, then we can validate and performance model optimize each module by itself. And in that sense, then reduce the work on validation and efficiency improvement whenever we repurpose the code. And this actually worked very well. So the quantum code library, as we call it, this quantum transport code, proved over the years to be scalable from notebooks to supercomputers, even beyond 130,000 CPUs. It is, of course, very much object-oriented coding. It is involving arbitrary level of MPI parallelization. Of course, there's some professional software development aspects like automatic code documentation in there. But most importantly, the code is really flexible. So I'll try to showcase that now in the next couple of slides, with some examples. So when you recall those validation examples I've shown you for sketching self-energies, they were all on 3D materials like 3-5 semiconductors. We did the same also, of course, with silicon and germanium. Now, in those cases, the electrons have been represented in atomistic tight binding. Of course, we did that also in effective mass. But obviously, there's new materials that are attracting a lot of attention, like transition metal decalcogenides. Now, they are in that sense special, at least from the point what I've shown you so far, that they are not that well representable with atomistic tight binding. So in order to in particular cover the van der Waals coupling between the layers accurately. We switched towards a DFT-based representation. We actually used maximum localized Fourier function Hamiltonians for that. And in that sense, you could say it's a very different Hamiltonian. So, the typical situation would have been now we have to validate our sketching self-energies once again, because they're in such a different shape now. Well, with the propagation concept, we did not have to do this. We just applied the same methods right away. Given again, they were given in position space. It was literally a very straightforward way to do that. And what you see here is just some examples taken out of this fairly recent paper. There we actually also included remote phonon sketching. So what you see here is the Urbach parameter as a function of the number of layers for here 3 of those TMDs when they are in the vicinity or like capped with different dielectricals or different oxides. So obviously for device engineers, it's important to know, which of those oxides to use. And obviously, we have for these oxides different optical, soft optical modes, soft polar modes, and then they have different impact on the mobility properties in the TMDs. Then just the same way, like with this maximum localized Fourier functions, we also compared against experiments. This was done in collaboration with the experimental group in Northwestern University. So they had data of anti-ambipolar behavior in molybdenum disulfide black phosphorus interfaces. So you can see here the experimental IV characteristic. There is here this peak in the IV around 0 gate voltage. So for this case, since the molybdenum disulfide is, electron dominant, so conduction band transport, black phosphorus is hole dominant, so with p-type, so with transport in the valence band. So when we have a high current density, we expected at that time there should be then a significant electron-hole recombination. Now, that's a word of caution again when you work on an EGF. If you do a straightforward implementation of electron photon interaction, you would have to solve polarization diagrams, so these kind of bubble diagrams, and they are computationally very expensive. I mean, at least from an industrial perspective, they are literally prohibitively expensive. Technically, the reason for that is that with these additional, sketching vertices, you have too many high-dimensional integrals to solve. Even like when you try hard with solving them analytically, it is just really painful. So a good way to avoid that load is, applying the Whittaker probe sketching method. We had expanded that in this paper and some others to cover electron-hole recombination and generation. So in that sense, we can model the interaction of photons, whether you have photon emission or absorption, or also even non-radiative interband transitions. And that method originally was developed within the propagation concept for atomistic tight binding, but here it is now transferred towards these Fourier function representations. And yeah, we had a very nice agreement, at least a qualitative agreement of this anti-ambipolar behavior with the experiment. Yeah, we didn't have a quantitative agreement simply for the fact that the experimental device had lengths of several micrometers. So that is just too much in atomic resolution. We were able to go up to 40 nanometers, but at least we were able to reproduce the trends and identify different transport regimes. When we go a bit deeper into optical devices, we had also worked on light emitting diodes. Now these structures are even larger than those 40 nanometers. So, we typically had to include simulation domains up to 120 nanometers. These are here data in atomistic tight binding, because these are, this is here a calculation of a blue LED. So this is a gallium nitride, indium gallium nitride based. Now in those cases, again, we have obviously a very significant electron-hole interaction. We need that to predict the light emission. Even for the Whittaker probes, the system is a bit too long. So what we developed was a hybrid model. So in the perspective of those earlier slides, I would say now this is a new approximation that we hadn't envisioned when we introduced the propagation concept. So what this hybrid model does, of course, details are given in the paper, but just in short, it allows the users to define areas that have, well, a lot of, a high electron scattering probability, so they might be thermalized because of a fairly small potential drop. So one would maybe take this region here that is heavily doped, like so, N and P doped areas, and then also those quantum wells that trap a lot of electrons on holes. They would be considered as equilibrium areas, and areas in between, like these barriers, then they would allow just for ballistic tunneling between these islands of equilibrium. And each island, each domain of equilibrium would have its own local Fermi level and temperature. And the method overall will then allow to determine all of these Fermi levels so that overall current conservation is fulfilled, including when there is a recombination current. So this is a multi-domain treatment, but still the propagation method handled it very well. So like concepts like recursive Green's function method were just applicable here out of the box. The developers only had to worry about doing the nonlinear iterations until these Fermi levels and the current conservation were given. So this was very successful. Also here, we got comparison against experiments, at least in the current density. Now here I have to admit there was some fitting involved, namely for the contact resistance. So of course, at some point you would get here into a metal and that was not part of the simulation domain. But that basically shifts this IV characteristics only here versus the bias. Otherwise, we just get very nice agreement. And with this multi-domain model, we were also able to help industry with determining which of those quantum wells is emitting how much of light under different current amplitude conditions. Yeah, maybe another example for this flexibility of the code of this propagation concept. Of course, we also worked on topological insulators, including magnetic fields. Yeah, I thought one thing to mention here, in case there's some people in the audience that work on that topic, I thought it's worth to mention, as far as I understand, the work in this field is often envelope function approximation models are applied, like K2P methods. So I'd like to advertise atomistic approaches instead. So when we worked on bismuth telluride nanowires for quite large cross sections, actually, of course, we had seen surface states. Some of them here are depicted here on the right. But we had seen, when you look at these nanowires in their growth direction, yeah, you have surfaces of different atom types. So I should mention, you see here these dots in blue, kind of greenish and red. Red here is bismuth atoms. The blue ones are those tellurium atoms that have only tellurium atoms as neighbors. And this turquoise or greenish color, these are the tellurium atoms that see both bismuth and tellurium. Yeah, so just simply because of the geometry of growth, these nanowires surfaces, they have different chemical environments. So you have one facet that is kind of mixed in the atom type and one facet that's pure tellurium one. So, obviously then when you look at the surface states, they will see different dispersion relations on, depending on which surface they are. And that effectively means if you look here at the position just on the circumference of the nanowire, you will have an effective potential that has some barriers. So like here, the tellurium one surfaces, they could be effective barriers to the surface states, contrary to the mixed surface areas. Of course, also those, like the energy differences here and the dispersion, this is a matter of design. So if you change the geometry or the growth, like the cross section, you will have a different in-surface confinement of those surface states. But of course, you can see that only if you do at least once an atomistic simulation. And yeah, by the way, also to mention, of course, we cover magnetic fields in atomistic models with the Pios phase. Yeah, most of my team's work, at least for quite a while, was also focused on band-to-band tunneling devices. In engineering in particular, TFETs are considered very interesting candidates for future transistors because of their steep slope. So fundamentally, they can be steeper than the well, standard transistors. They would have a limit of 60 millivolt per decade. TFETs can go below that, so can switch faster. So in general, when you want to model these kind of devices, you might face a kind of traditional charge model, which would consider a delimiter line between valence and conduction band. And then you would typically assume that all electronic states to the left of the delimiter line and below are valence band states. So in that sense, they're holes, they are positively charged in that sense, and everything on the other side is negatively charged. Now that model works very well if you have a clear separation between valence and conduction bands, not just like in many optoelectronic devices. But when you have very steep transitions between conduction and valence band, then you will have states that have a significant mixture between conduction and valence band. So in the end, this delimiter model is ambiguous and should be avoided. So what we had used is we borrowed basically the approach of density functional theory methods. There you would consider all valence band states to be electronic. Yeah, that is quite difficult because there's a lot of valence band states to consider. So each of those would have its own band edge. Of course, then you have van der Hoeven singularities. If you try to resolve them in a real energy mesh, even 30,000 points are not sufficient. So, you know, we discussed it in this paper. You would have to go to a very, very large number of energy points just for all the equilibrium background energy or electron distribution. Now, because of the flexibility of this propagation concept, we were able to apply the Cauchy residual theorem. So, you know, we basically consider complex energies and then do the contour integral, you know, to cover occupancy in vast energy ranges. And it turns out that that converges extremely well. Just 30 points alone were enough. And the reason behind it is, well, you have those resonances, the van Hoeven singularities. If you remember earlier the slide on the poles of the Dyson equation, they are fairly close to the real energy axis. So if you're deep in the complex plane, these poles are very, very shallow and broad, and in that sense, very easy numerically to resolve. Yeah, so we validated that, of course, and we were able then for TFETs to showcase, you know, significant differences in the IV characteristic once you have the unambiguous treatment of transport. Yeah, maybe I do it a little quicker. I mean, I just wanted to mention that we, of course, can do that for other particle types. So we've done, we have applied this propagation method also on phonon transport. Not to go too much into details, but if you care about thermal transport, phonon-phonon scattering is really important. Standard method for that would be the non-equilibrium molecular dynamics method. So, you know, if you're aware of this method, there is one shortcoming of the method. It requires a position space treatment of the device, even when there are periodic directions. So this is just because it's difficult to introduce a periodicity parameter. NEGF, of course, allows for that, but when you speak with people in the community, most likely you will hear that, yeah, NEGF doesn't work well because it doesn't cover scattering. So when we had here done a comparison of interface thermal resistance, depending on the interface mass ratio, the molecular dynamics results are here the blue ones. The green ones would be the ones you would typically find in that community when people apply, well, basically the Landau approach, so ballistic transport. Now we've expanded the Whittaker probes again to avoid those polarization diagrams, so these complicated or expensive self-energy simulations to handle phonon-phonon scattering. And well, we got very nice agreement with the non-equilibrium molecular dynamics, but for a fraction of the numerical costs. So it's just as an advertisement, NEGF does very well also for phonon transport if it's done well the right way, like at least covering all the scattering and still being efficient. Yeah, are there actual users? Well, this is just a shout out, also kind of advertisement if you're interested in our work, you use it yourself. So all of the work you've seen and way more than that entered the quantum code library of Purdue. That's literally a toolbox of hundreds of simulation modules. It's really massive. So it was about 65 authors, most of them PhD students that contributed to this. Yeah, you can get a license to that either by contacting the Office of Technology and Commercialization, or just let me know and we can discuss the details. the most famous product or derivative tool out of the quantum code library is NeMo5. It has quite a significant usage. It is powering 6 tools at NanoHub with really lots of simulation runs every year. If you want to have a smooth custom and usage experience, kindly refer to the Silvaco company. They are providing a very streamlined version called Victory Atomistics. We are currently expanding that towards material science, and I'll mention it in next coming slides, and towards also chemistry. And again, you can compose your own tools out of that. You wouldn't be the first one to do it. So actually already almost 10 years ago, when we worked a lot with the Intel company, they adapted the code. Fairly recently, some years ago, they had published a comparison of simulations with their own experimental data. So this was done with the NeMo5 code, and in the same paper, you can actually even find their simulation tool setup in-house. And you can see here, there's a classical, semi-classical, and quantum level of simulation. The quantum level is indeed NeMo-based. So all of those features we have is in NeMo5. And of course, we reproduce this with our current work with the Silvaco company to make it available to a broader user base. We are expanding the quantum code library at the moment towards several new devices like these nanosheets and carbon nanotube transistors. This is actually already done by now. So yeah, we hope to see even further increase in usage. So what can we do in material science? Well, that goes back to work for the Semiconductor Research Corporation about 8 years ago. At that time, we wanted to expand the non-Euclidean Green's function method to handle non-trivial leads. So if you look here as an example at a graphene nanoribbon, usually people would use maybe this here as their active device, and then they would continue that ribbon just with the same thickness into minus and plus infinity and have those sections as their leads. Of course, this is useful, but experimental reality often has not such simple leads. So for instance, you could have leads that just widen in their diameter with increasing distance to that, let's say lead device interface. And yeah, we expanded the NEGF methods to handle such non-trivial leads. By the way, validation, of course, again, very important. So what we did is we looked at the same physical device, but interpreted differently numerically. So once we just said, okay, let's have this as the central device region and contact cipherentry is just on those lines. Or in the second case, we have a larger numerical device and take those lines as the contact interfaces. Of course, numerically these are very different in size and geometry. Cipherentries look very different, but physically it's supposed to, it is the same. So if you look at transmission, so probability for an electron to go from minus infinity to infinity, that better be the same. And you can see that we have to zoom in very deeply to find the difference in those two cases. And that has to do with convergence. So there's some iterative process involved with that. And if you push hard, then you get even further and better agreement. Now we expanded this method. Maybe I can go back. We expanded this method and allowed for one lead to just wrap around all around the central device region. What we gain with that is we can do material science all in position space. That method we call the recursive open boundaries and interfaces method, published some years ago. Of course, again, we validated this method to reproduce density of states of textbooks. But we also worked in an atomistic tie binding on graphene. So when you look at the density of states, there's a function of energy. Obviously, you would expect a Dirac cone, so linear dispersion, this is here in red. And indeed, if we make the lead environment around the central simulation region large enough, we can fairly faithfully reproduce this linear dispersion. So what is interesting in graphene, when we do it all in position space, well, quite some years ago, there was a report that said, if you dope silicon with 3%, when you dope graphene with 3% silicon, then you will get a band gap. So graphene with a band gap. Obviously, this is very exciting. This was experimental work together with some simulations. The simulations assume periodic boundary conditions. Of course, in reality, silicon is randomly distributed. So we looked at that system. First, we applied Robin on 3% periodic distributed silicon. So indeed, we reproduced the reported band gap and the simulated band gap in that work, I should say. So you have here density of states as a function of energy. You can see here the band gap. I show you here two different results simply to show again the convergence issue. So it's a challenge. In particular, close to the band gap, you see here some beating pattern that gets smaller the more atoms you include in that environment. You see here, by the way, 282 lines because our simulation domain had 282 atoms. Overall, the simulation had 3 million atoms. So the vast majority was in those large leads. Then you zoom in into a section of those density of states lines. You can count here, there are 9 lines, but here are 3, 4, 5, 6, 7, 8, 9 lines. So those 282 density of states lines, they actually fall into 9 different groups. And that's, I think it's interesting. And it comes from the fact of the shape of this supercell. So this is here the 3% periodically doped with silicon doped graphene. So you would have here in the center a silicon atom, and then, well, that's the first atom type that you have here. Carbon atoms closer to that silicon will have, well, their unique chemical environment. So that's the second type. And then with increasing distance to that silicon, you will have a third, a fourth, a fifth, a sixth, a seventh, a eighth, and a ninth type. Those carbon atoms here, they have the same distance to center silicon as to the next supercell. So in that sense, 9 different atom types, we get 9 different density of states lines. That makes sense. But if you now envision, if we distribute those silicon atoms randomly, you won't have 9 different atom types, but just as many types as you have in your simulation domain. And that's what we indeed get. So here's density of states, a function of energy again. We get here 282 different lines, and that obviously gives us a lot of noise. That is true for if you have 3% silicon, also with 2 and 1%. So it's a lot of noise. But if you look here at lower density of states, you can see that all of those density of states lines, they faithfully reproduce the pristine graphene density of states. So this is a semi-logarithmic plot. That's why you have here the bending instead of just a nice linear shape. But you see here that increasing the silicon percentage, it gives you just a linear shift of the density of states. So this is a stark contrast to the case when we have 3% periodic silicon, but there we had a band gap. Here we just have a shift of the density of states. I mean, I think that the shift makes sense. I mean, 3% foreign atoms, I think should be just a linear response. That's exactly what we get. But if you apply periodic bounding conditions to that small perturbation, you get a massive difference. Maybe it's also worth to mention, by the way, the experimental work in that paper showed a work function shift of 130 millectron volts. So given the uncertainty in the silicon concentration, that actually quantitatively agrees with the shift that we observe here of the Dirac cone. Just to show a bit more how different the materials can be when you apply or when you approximate a symmetry. So you have here one simulation of a graphene disk with silicon. The silicon atoms here are given as black dots. The graphene, I mean, the carbon atoms are white, but since there's so many, you just see them as background. The top half of the disk has 3% random silicon, the bottom half periodic silicon. And well, if you zoom in into the density of states, you can see, I mean, at the Dirac point, indeed, the top half here has pockets of electron density. The bottom half is just the band gap. So again, the only difference between these two different disks is the periodicity assumption. So again, warning, please apply periodicity, assume the periodicity only when the system is truly periodic. With the Robin method, of course, we can avoid that and can have a more realistic modeling of materials. So maybe I'm running very low in time, but I'll try to give you at least a quick heads up what we do with liquids. This is work we do with the chemistry department. So the experimental colleagues have found that there is a set of chemical reactions that happen very slowly in bulk liquids, but they happen very rapidly in micro droplets. So of course, the assumption would be that once molecules are at the surface, that the geometry will somehow boost the chemical reaction. We do that in explicitly modeling thousands of atoms. We can do that with density functional type binding. We looked at a specific reaction, and the reaction rate we assumed is here given by the exponential function, the difference between the energies of the reactants and the highest energy transition state. And yeah, what we have seen because of the explicit discretization that depending on where charges are located, when you have a charged molecule, depending on how it is oriented towards the surface, and when the charge is either deep in the liquid or at the surface of the liquid, you have a very different energy landscape. And that energy difference, once it's converted towards the chemical reaction, namely when the molecule rotates during the chemical reaction, it gives you an immense surplus to the chemical reaction, like over 500 or 600 millectron volts. And that translates into a massive speed up because of the exponential function. But once you do then the right statistical weight, like this density matrices, it actually happened that we found a reaction acceleration overall of 10,000, which agreed fairly well with experimental data. Now we're expanding this, of course, towards other reactions like DNA base formation, and well, these data hopefully will get published very soon. So where does NEJF come in here? Well, if you want to simulate liquids explicitly, well, usually you would find in literature at some point simulation domains are truncated, so any wave function would have to end at that simulation domain. Everything beyond would be just electrostatic environment. That's for implicit models. We can have everything with this Robin method. It is explicitly discretized. We still have an end of a simulation domain, but wave functions wouldn't have to stop there. So in that sense, we will hopefully soon have millions of atoms instead of just a few thousand for more complicated surfaces and liquids. So what's next? Well, very briefly, we're expanding, of course, this quantum code library towards a lot of different applications. We do that a lot with industry. So we look at solid-solid interfaces, solid liquids, molecules in liquids, defects in solids in particular as well. We do a lot on the 2D electronic side, like piezoelectric systems, liquid gas interfaces. You've seen results already. And yeah, 1D transport channels, I think, are very appealing when they have very irregular networks. So I have to be rather short. So maybe I just keep the conclusion here. Reminder what you've seen as devices. I'm really happy to say that our past work has set nanodevice simulation standards in industry. Yeah, we try our best that our models are spurring innovations. And of course, we try our best to open new frontiers in chemical and pharmaceutical industry with their quantum transport methods. So thank you so much for your attention.
Yeah, thank you, Tillmann, for this wonderful talk. Very, very interesting results and very nice overview of your work. Are there comments, questions from the audience? Maybe I start with one. I have several questions. So in this work where you doped graphene with silicon, which Hamiltonian do you use for this description?
Yeah, here we use the simplest possible one, like just a PZ model for graphene atoms. I think it's fairly common. For the silicon, what we did is we just assume silicon atoms are behaving like graphene when they're embedded in the graphene lattice, but with a different on-site energy. And that on-site energy was actually fit so that we exactly reproduce the DFT data. And starting then from there, we wanted to see when you change the symmetry, what's the impact, right? When you change the periodicity.
So they're treated like point defects with a different on-site energy.
Absolutely.
Okay, I see. Why do you have only 282 atoms in the central device, but this about 3 million atoms in the leads? I did not understand this.
Yeah, that has to do with that convergence that you see there. So if you want to have a pristine graphene, then you could say a real space discretization is the worst possible way you would do that. But you would usually right away go to a momentum space, since it's a periodic system. So trying to resolve a periodic system, a crystalline system in position space is expensive. And what we do is well, we have a certain focus area. Maybe I actually try to use this here instead of my hand. So you have this focus area, and at some point you have to stop discretizing the environment just because it's getting too expensive numerically. So what we do is we try to push this boundary as far as possible to have a well-converged result here in the center simulation domain. There is also a complex absorbing potential that one has to add to that, so that interference effects you would have because of hard boundaries do not play a significant role in here.
The leads also contain silicon
for the non-pristine case, of course, yes. You discretize 3 million atoms, including whatever symmetry or non-symmetry the system will have, yes.
Okay, now I understand.
So if you move a few of those atoms somewhere, of course, the self-energy at this boundary will change.
I see. Okay, yeah, a related question. You showed how this, you showed here, it's this example that the leads are made from, actually the same material as the central region. But I think 2 or 3 slides before, you showed this example of this carbon nanotube transistor. And there, the leads are made from a very different material. The leads are just, metal droplets of metal atoms in contact with the carbon nanotube. So how do you simulate such a situation, which is depicted here, let's say it's the bottom left?
Yeah, so the typical way that, well, community does, also industry in that sense, is you would just assume ohmic boundary conditions. So you'll basically only consider the gated region with some area surrounding that, but effectively the tube would just continue infinitely. Now, with the general lead method we have, you don't need to do this. You can have Schottky contacts and you can consider the transport through them explicitly. What is challenging with that, however, is how you treat the Poisson equation. As soon as you have a metal, obviously, you have to assume it's screening with instantaneously, basically. But as such, if you know the potential profile for electrons to get into source and drain contacts, you can directly put that into the simulation domain.
Okay.
So, I mean, like if it's a concrete question, like a research question, what we would do is then, well, I guess maybe DFT simulations, if that's doable for specific metals, read from there what the effective potential profile electrons will see, like what work function they will see, what's the shape of what's the thickness also of the Schottky barrier, on the height, obviously, and that we can impose.
I see. Okay, I think there is a question in the chat. So Jose Juan Ramos is asking, what about time crystals? This is only what he is writing.
I'm not an expert in this, so I don't want to claim now, but I mean, there's, I guess, 2 points of this. Unusual symmetries in general, we can handle that because of the explicit treatment. So let me see whether I actually have backup slides on that regard. Let's see. So here is some calculations of twisted bilayer graphene, just with different angles. So you get your periodic cases, and also you get quasi-crystalline cases. Both of those simulations are treated just the same way. You only have a different structure. So as far as I understand time crystals, pardon if that's not really helpful, but at least I'd like to mention that. Time domain as such, we had a colleague who had used our code for time-dependent quantum transmitting boundary simulations. So that's, was nice to have, but they were not as mature that we really supported that for users. So it's possible to expand the code towards time domain, but I wouldn't claim it has been finished.
Okay. Yeah, just you have this as you have this transparency here. Can you go here to smaller angles, to the magic angle?
Oh yes, sure. Absolutely.
Okay.
Yeah.
Okay. Yeah, are there further questions, comments from the audience? I will continue with some questions.
Sure.
So at the beginning of your talk, you gave this introduction to the Green's function method and explained us the importance of the effect of the self-energies. My first question is, well, there are, depending on the type of interaction, there are different types of self-energies and different models for these self-energies.
Sure.
So in this quantum code which you are using, which models do you use and which types of interaction do you can in general take into account?
Okay, so we do support self-consistent Born approximation, and we support critical probes. We have also some, I would say, more debugging type self-energies, which are just constant, like constant numbers. As such, anyone could define any matrix themselves, and use it as a self-energy, or even a complicated algorithm to define those matrices. And whether these algorithms would then need Green's functions as an input from maybe the code itself, or maybe from somewhere stored somewhere, or given by some other tool, it doesn't make a difference, right? It's again the flexibility of the propagation concept. So in that sense, if you want to have polarization diagrams, for instance, solved, or maybe even vertex corrections, go for it. I mean, I can tell you it will be expensive, but again, it also strongly depends on how much effort you put in. But yeah, what we have currently in the code is self-consistent Born and critical probes.
Self-consistent Born for the electron-phonon interaction.
And for electron impurity interaction, for remote phonon scattering. I think we started also for roughness self-energies. So that as such is there. I think we were not too happy with the validation yet. That's why we don't support it yet. But yeah, as such, there's like whatever you like.
I see. Yeah, related question with this. Then you showed this integral equation for the self-energy. For which type of? This was the electron polariton.
No, it's a polar optical phonon.
Okay.
So this is just one example out of this paper. I hope the reference is here, like this 2019 one.
Okay. And you said that you tried to solve analytically this integral.
Oh, we did.
How can you do this, as the integral depends on GR and G less?
Yes, that's true. But you can see the dependency of this integral. I mean, there is this momentum transfer and there's change in energy in here. But well, the phonons we assume here are plane wave phonons in all three directions. So in that sense, the phonon Green's function is analytically known for that specific case. And that allows you to solve the integrals over the phonon momenta that are not explicitly part of the electron Green's function.
I see.
So again, that's a reason why when you have, let's say, 2D systems, you will have a different formula than when you have a nanowire, or when you have a bulk or like a layered structure with two periodic directions. So yeah, for all of those different periodicity situations, you will have to derive new self-energy formulas from the fundamentally the same equation, just to reduce the burden for each of the situations as much as possible.
I see.
So in that paper, you will find quite a list of equations for sketching on phonons as well as on impurities.
I see. Okay.
Yeah, and we had to validate each of the self-energies individually, like for each situation. So this is quite a lot of work, but it's definitely worth it once the code is repurposable.
Of course. Okay. Yeah, are there further comments, questions from the audience? If not, I have a last question. Can you tell me some words, not on your talk, on these classes of ideas to invention?
Innovation.
What is it about? Innovation.
Yeah, this is an exciting new program we have at Purdue. We support in particular students from industry, like they finished with a bachelor, we help them within a year to increase their education to the master's level, so they can graduate with a master's within a year, independent of research projects. So in that sense, they, within this innovation ideas to innovation class, they can identify their own project, so they will find a problem in society. I don't know, maybe with people that are aging, they might need engineered devices to support their daily life, and just to take one example. Or maybe we had also teams like that worked on devices to prevent forest fires for spreading, or even preventively, like to identify fire fuels in forests from LiDAR data. So first, students have to identify a problem of society, then they have to think about possible solutions, they have to propose a product, they form teams, they de-risk that product idea with an actual senior design, like a real product, a demonstration that they have to produce, and then in the last semester they have to assess the market, they do customer interviews and pitches and an investment plan in that sense, or a product development plan. So this is mimicking basically a product development process in industry.
I see. So these are mainly engineers,
These are all engineers, yes. The different disciplines, but this is an engineering class.
Okay. That's a nice concept.
I'm excited about it, yes. This is
that's a very
fully advertisable.
Okay, yeah. Are there further comments, questions from the audience? If this is not the case, then Tillmann, thank you again. Thank you for joining us, at least virtually today. See you next time in person. Yeah. See you next time in person, and yeah, bye-bye. See you next